Hello there, this is Dr. Armand bringing you another exciting lecture in Gen Chem 2. We're continuing our lecture series on colligative properties. In this lecture, we'll be discussing the colligative properties of freezing point depression and osmotic pressure, and looking at some examples involving those different colligative properties. So sit back and relax and enjoy the show. So first off, we're going to warm up with a practice problem of a previous colligative property that we talked about. We talked about Raoult's law, which deals with vapor pressure, and boiling point elevation, which deals with solutions raising or elevating the boiling point of a solvent. So in this problem, the boiling point of a solution consisting of 11 grams of a non-electrolyte. So it's important that we note that it's a non-electrolyte. We'll discuss later about strong electrolytes and how they can affect this. And 145 grams of water is 100.1 degrees Celsius. What is the molar mass of this non-electrolyte? So we want to know, we have this non-electrolyte. We want to know what's the molar mass of it. And so before we begin, if we look at the equation for molar mass is the mass divided by the moles. So in order to calculate molar mass, we need to know the mass and the moles of our non-electrolyte. Well, the mass of our non-electrolyte is 11 grams. The moles of the non-electrolyte is what we don't know. So now we have to use the other information to calculate moles. And so what equation comes to us that relates boiling point and moles? That's correct. It's delta TB equals KB times the molality. And if we remember from earlier in this chapter, molality is moles of solute divided by a kilogram solvent. And so if we want to solve for moles of solute, is molality times kilogram of solvent. So in order to calculate the moles of solute, we need to know the kilograms of solvent, which we do. It tells us that we use 145 grams of water, so that'd be 0.145 kilograms of solvent. And we need to determine the molality of the solution, because once we know the molality, we can find the moles. Once we know the moles, we can find the mass. So now we have to rearrange this boiling point elevation equation to solve for molality. And so molality equals delta TB divided by KB. So the molality, so in order to solve this, we need the KB, which is given to us, and we need the delta TB. Now delta TB is the change in temperature between the solution and the pure solvent. Now it doesn't give us the boiling point of the pure solvent because it's water. It's understood that you know what that is. And so it's going to be the solution's boiling point minus the boiling point of the pure solvent. So that means the change is 0.1. So now we have the KB, we have the delta TB, which is 0.1. Now we can solve for the molality. So molality equals 0.52 divided by 0.1. And that equals 5.2. So the molality of this solution is 5.2 of this non-electrolyte. Now that we have the molality, we can find the moles. So moles of solute equals the molality times the kilograms of solvent. And we get 0.754 moles. Let me double check. Yes. So now we have the moles of non-electrolyte, so we can solve for the molar mass. So anytime you're solving for molar mass, this is the way that you would do it. And we get 11 divided by 0.754. So we get that this non-electrolyte has a molar mass of 14.59 grams per mole. So let's just double check here. So kilograms of solvent, that's correct. The KB, correct. Yep, so the molar mass is 14.59. All right. So moving on. Now we're going to talk about freezing point depression. And so freezing point depression, what happens is when you add a solute to a solvent, it lowers the freezing point of that solvent because now you have stronger intermolecular forces between the solute and the solvent versus just the pure solvent. And this goes back to Raoult's law because all these laws are kind of interdependent, is because when you add a solute to a solvent, it lowers the vapor pressure of the solution. So now the solution freezes at a lower temperature than the pure solvent. And just like with boiling point elevation, as you look here, this is the normal melting point of the solvent. Now when we add a solute, you see that the normal melting point decreases because now you have that solute, you have these stronger intermolecular interactions. And just like with boiling point elevation, the change in the freezing point temperature is proportional to the molality. So we use an equation similar to delta TF equals KF times molality. But here notice that delta TF is the freezing point of pure solvent minus the freezing point of minus the freezing point of the solution. So notice it's flipped when compared to the delta TB. So delta TF is the pure solvent minus the solution. And just like with the KB, you have a series of KFs for all the different solvents, and you have their corresponding melting points. Now it's understood that if you have water, that you know its freezing point, melting point is 0 degrees Celsius. But you don't have to remember any of the other melting points for the other solvents, or you don't have to remember the KFs. Those are typically given to you in a problem on an exam or homework, or a quiz, excuse me. So now let's look at some problems involving freezing point depression. So now we want to know what is the freezing point of an aqueous solution of a non-volatile solid that has a boiling point of 102.5 degrees Celsius. So again, to solve for the freezing point of the solution, we know that delta TF equals KF times molality. So in order to, and we know that delta TF equals a TF of solvent minus the TF of solution. So in order to find the freezing point of the solution, we need to take delta TF TF of solvent minus delta TF. And since we're dealing with water, we already know the TF of solvent. It's equal to 0 degrees Celsius. So we know that. We just got to find delta TF. So to find delta TF, we need to know the KF, which we do know, it's 1.86, and we need to know the molality, which we don't know. So now we have to use the other information given to us to determine the molality of this aqueous non-volatile solute. So what we're going to do is we're going to use the boiling point elevation information to determine the molality of this solution. So again, molality equals delta TB divided by KB. We know KB is 0.52. We know that delta TB is the boiling point of the solution minus the boiling point of pure solvent. And since we're dealing with water, we know that that is 100. So delta TB equals 2.5. So now we can solve for molarity. Molality equals 2.5 divided by 0.52. So molality equals 4.81. So that's the molality of the solution. Now that we know the molality of the solution, we can calculate delta TF. So delta TF equals KF times 4.81. And so we go delta TF is 8.95. So now we have delta TF. We can calculate the TF of the solution, which is the freezing point of pure solvent minus 8.95. So we get negative 8.95 degrees Celsius. So that is the freezing point of the pure solvent. Notice though, don't stop at this point. So don't stop here. That's not right. You got to then subtract it from the freezing point of the pure solvent to get to negative 8.95 degrees Celsius. Most students stop at this point. You don't want to stop here. You want to go and subtract it from the freezing point of the pure solvent. This is the final answer. In our second example involving freezing point depression, we have 17.5 grams of an unknown molecular non-electrolyte compound. So we know that we have 17.5 grams of this non-electrolyte in 100 grams of water, and it was found to have a freezing point of negative 1.8 degrees Celsius. We want to calculate the molar mass of this unknown compound. Again, this is a very common calculation in freezing point depression. In this case, it gives us the freezing point of the pure solvent, the KF, and we know that delta T equals the molality times KF. What we also know is that molar mass equals the mass divided by the moles. So to calculate the molar mass, we need to know the mass, which we do know, and the moles, which we don't know. So now we have to look at our delta T equation and say, hey, what in there deals with moles, and that is molality. So molality equals moles of solute divided by kilograms of solvent. So if we rearrange this, we get the moles of solute equals molality times kilogram of solvent. So do we know the kilograms of solvent? The answer is yes. We use 100 grams, so we can convert that to kilograms. Do we know the molality? The answer is no. So now in order to calculate molality, we look at this delta T equation. We know that molality equals delta TF divided by KF. So molality equals, before that, do we know KF? The answer is yes, we know KF, 1.86. Do we know delta TF? The answer is no. And so remember, delta TF equals the TF of solvent minus TF of solution. And so we know both of those. We know the TF of solvent and we know the TF of solution. So delta TF is equal to 0 minus a negative 1.8. So delta TF is 1.8. So now we know delta TF, we know KF, we can calculate the molality. So molality equals 1.8 divided by 1.86. You get 0.9677. So now that we know the molality, we can calculate the moles, because moles is equal to molality times kilograms of solvent. So moles equals 0.09677. So now we know the moles, we can calculate the molar mass. The molar mass equals 180.8 grams per mole. So again, whenever you're asked to calculate the molar mass of a compound, you need to know the mass and the moles. Generally, the mass is given to you. You have to find the moles, so you have to use the other information given to you in the problem to find the moles of your, for example, non-electrolyte. And then once you know the mass and the moles, you can calculate the molar mass. So now we're moving on to the last type of colligative property, which is osmotic pressure. And osmotic pressure works by the movement of solvent from a high area of concentration to a low area of concentration. But we're talking about the solvent, not the solute, and it passes through this semi-permeable membrane. So, for example, if you have pure water and you have a salt solution, water molecules will move from the pure water into the salt solution. So the level of pure water goes down, the level of the salt solution goes up until you reach the osmotic pressure. And so if you apply more than the osmotic pressure, you do reverse osmosis, where water goes from a region of low concentration to high concentration. So this is what osmosis is. So osmosis is the movement of water molecules from a region of high concentration of solvent to a region of low concentration of solvent. And this pressure difference that results is the osmotic pressure. So here we have pure solvent on this side. We have solution, so the water moves through the membrane to the solution. The level of solution increases, the level of solvent decreases. The difference in those is the osmotic pressure. So you have to apply the osmotic pressure so that you don't increase the level of volume for the solution. But if you apply more than the osmotic pressure, you get reverse osmosis, and that's how reverse osmosis filtration systems work. And so the osmotic pressure pi is proportional to the molarity of your solution. So the greater the molarity of your solution, the greater the osmotic pressure. And so the way we find osmotic pressure is similar to the ideal gas law that you learned about maybe a semester ago. And so the osmotic pressure is equal to the molarity times RT. So R is the gas constant, T is the temperature, M is molarity. Now the gas constant makes it that the osmotic pressure has to be in atmospheres. Again, the osmotic pressure has to be in atmospheres because your gas constant that you use is in atmospheres. And temperature has to be in Kelvin. Again, temperature has to be in Kelvin. And so we can use this equation to solve for the osmotic pressure or solve for the concentration when given the pressure. So again, T has to be in Kelvin. R is the universal gas constant, which is 0.0821 liter atmosphere per mole Kelvin. And this is the equation we use to calculate osmotic pressure or to calculate the concentration of a solution. So here we have a pepsin, which is an enzyme in the intestines of mammals that breaks down proteins into amino acid. We have a 12 milliliter aqueous solution that contains 0.2 grams of pepsin, and the osmotic pressure is 8.98 torr at 27 degrees Celsius. We want to know what is the molar mass of pepsin. So again, pepsin is an enzyme. Enzymes have very high molar masses. So what we need to remember is that molar mass equals the mass divided by the moles. So here we have the mass of the solute, but we don't know the moles of solute. That's our question mark. So if we can find the moles of solute, we can find the molar mass of this enzyme. So in the other information given to us, we're given osmotic pressure, and we know that osmotic pressure equals, I'll just write pi for the capital pi, equals MRT. Yeah. So when I write capital pi, pi equals, pi represents this symbol. Because I can't draw it all the time. And so in this equation, molarity is something that relates to moles. So we know that molarity is moles divided by volume. And so if we're solving for moles, equals molarity times volume. So do we know the volume? Yes, with 12 milliliters, it has to be in liters. Do we know the molarity? The answer is no. So now we have to use the information, other information, to determine the molarity. So what we're going to do is we're going to rearrange this osmotic pressure equation to solve for molarity. So do we know pi? The answer is the osmotic pressure. The answer is yes, 8.98 torr. Do we know R? The answer is yes, 0.0821. Do we know temperature? The answer is yes, 27.0 degrees C. But before we plug and chug, we have to convert torr to atmosphere, so we divide by 760. And we get 0.011816. Make sure you keep quite a bit of significant figures on the pressure. And now we have to convert temperature to Kelvin. So that'd be 300 Kelvin. So now we have the osmotic pressure, we have the R, we have the T. We can calculate the molarity. So let's do that. So molarity equals osmotic pressure divided by R times T. And I get a molarity of 0.48033. 333 times e to the negative 4. Let me double check. Yeah, that's right. And your values may differ depending on the rounding, but somewhere around in there, 4.8 times 10 to the negative 4 molarity. So now we know the molarity, we can calculate the moles. So moles equals molarity times the volume. And it would be 5.7640 e to the negative 6. Let me double check. Yep. So now we know the moles and we know the mass. We can calculate the molar mass. And again, this may be a very large number because it's an enzyme. It's okay. And we get 34,698 grams per mole. Let me double check. Yep. And so that's the molar mass of this enzyme. So again, we're doing the same thing. When we're looking for molar mass, we need the mass in the moles. Generally, the mass is given to us. We use the other information to find the moles. Well, the other information dealt with osmotic pressure, and the thing that deals with moles with osmotic pressure is molarity. So to calculate moles from molarity, we need the volume and molarity. So then we rearrange the osmotic pressure equation to solve for molarity. Once we have molarity, we can calculate moles. Once we have moles, we can calculate molar mass. But again, make sure your osmotic pressure is in atmospheres and make sure your temperature is in Kelvin. Another problem involving osmotic pressure and actually freezing point depression. So here we have this fructose solution, has a density of 1.049 grams per centimeter cubed, has an osmotic pressure of 17 atmospheres at 25 degrees Celsius. Find the temperature at which this solution freezes. And it gives us the Kf and the molecular mass of fructose. So again, to find the freezing point of solution, the Tf of the solvent Tf of solvent minus delta Tf. So do we know the Tf of solvent? The answer is yes, it's 0 degrees Celsius. Do we know delta Tf? The answer is no. So we need to find delta Tf in order to calculate the freezing point of this solution. So delta Tf, what's its equation? Delta Tf equals Kf times molality. Well, do we know Kf? The answer is yes. Do we know molality? The answer is no. So in order to find molality, we know that molality is moles of solute over kilograms of solvent. So what we have to do now is we have to use the information in the first sentence to help us determine molality. So this 17 atmospheres, 25 degrees Celsius, 1.049 grams per centimeter cubed. What we're going to do is we're going to use this to calculate molarity, because we know that pi equals MRT. To solve for molarity, we need molarity equals pi divided by RT. Once we find molarity, then we can convert it to molality like we did at the beginning of chapter 13. So do we know pi? The answer is yes, it's 17.0 atmospheres, and it's already in atmospheres, that's good. We know R, 0.0821 liter atmosphere per mole Kelvin, and the temperature is 25 degrees C, and it's 298 Kelvin. So we have all the ingredients to solve for the molarity. So let's go ahead and do that. So molarity equals 17 divided by 0.0821 times 298. Molarity equals 0.69485. Make sure you keep quite a few significant figures. So now we know the molarity. So we have to convert from one unit of concentration to another. So once we know molarity, we need to assume 1 liter of solution, which is 1,000 milliliters of solution. So if we assume 1 liter of solution, we know that the moles of solute is 0.69485. Now, if we know the moles of solute, we can find the mass of solute, because we can take the moles times the molar mass. We get 125.2 grams of solute. Now we need to find the mass of solvent. So we need to convert the volume of solution to mass of solution. So mass of solution equals the density times the volume, but volume needs to be in milliliters. So the mass of solution equals 1,049 grams. So we have the mass of solution. Now we can find the mass of solvent, which is 1049 minus 125.2. $923.8 grams. And we're going to convert that to kilograms. So now we have the mass of solvent, we have the moles of solute, we can calculate the molality. So molality is moles divided by kilograms of solvent. So now we have the molality, we can find delta TF. So delta we get 1.4. That's delta TF. Now we have to find the freezing point of solution. So TF of solution equals 0 minus 1.9. This would be negative 1.9. So that would be the freezing point of this solution. And this is in, again, degrees C. So again, when you make it this far, you find delta TF. Excuse me, not 1.9, it should be 1.4. So 0 minus 1.4 equals 1.4 degrees Celsius. Negative 1.4 degrees Celsius. So again, most people get to this point, they find delta TF, but then they forget to subtract it from 0 to get the freezing point, which is negative 1.4 degrees Celsius. So just to recap, we're looking for the freezing point of the solution, which is the freezing point of solvent minus delta TF. We have the freezing point of solvent, we didn't have delta TF. So to find delta TF, we need the KF and molality. Well, the KF is given to us, the molality we don't know. So we have to find, which molality is a unit of concentration, we have to use the other information given to us to get the concentration of this solution. And that's where we use the osmotic pressure equation to give us the concentration in molarity because we know the osmotic pressure and temperature. So once we found the molarity, we converted it to molality. That's what we did in the middle here. We convert to molality. Once we found, or excuse me, yeah, once we found the molality, we found delta TF. Once we found delta TF, we found the freezing point. So this concludes reviewing over or explaining the different colligative properties involving non-electrolytes. We'll next be looking at colligative properties involving electrolytes and how that changes the equation just a little bit by adding one more parameter to the equation. So I hope you enjoyed the video. Maybe you learned something new. If you did learn something new or you enjoyed the video, make sure you hit the like button. And as always, until next time, Dr. Armand signing off.